In general, floating point numbers are real numbers, and these are different numbers than the currency. Floating point numbers are basically they different in binary form than any other sort of numbers. The data type in VB, which is single or double, are actually floating point numbers. How do we represent these floating point numbers? Need to be understood properly in terms of binary. First of all, in binary numbers, we don't have floating point. Floating point means as computer we cannot actually have a space for a point, so we have to float the point to a fixed space. We will learn about it, and then we assume that point lies between these two first bits or whatever, and we do not actually show it. So that is floating point. So first we have to find the fixed point. Now what is fixed point? As in शहजादी ये यहाँ से let's say in our number system, when we have a point, we write it like this: 10.5, 135.36, 2005.408. What is actually happening that this point is fixed at its location. Okay? This point is fixed at its location. This is called fixed point. And how do we come up with this fixed point? This is 10 to power 0, 10 to power 1, 10 to power 2, 10 to power 3, and we go further. Over here, this is 1 over 10 to power 1, 1 over 10 to power 2, and this way it goes further. By the power of 10, it is increasing on the left, and by the power of 10, it is decreasing on the right. Same phenomena is here. Now, what's happening is, see, this is the point. On the left, it is increasing by the power of 2, and on the right, it is decreasing by the power of 2. Alright? But the thing is that in our number system, we have fractions reducing by the power of 10. Means that we would have more denominations in fractions than in binary. What happens in binary is when we go from one fraction to other, what happens that the number got reduced by half. और हमारे पास वहाँ पे क्या होता है बाइनरी में हम उसको 10th तक लेवल तक लेकर जाते हैं. So that actually gives us the point that we cannot actually show so many things, so many numbers in between. We will look into that. So if we go on the left of the point, this would become 1, 2, 4, 8, 16, 32 as usual, the left. And on the right side it becomes 0 0.5, 0 0.25, 0 0.125, 0.0625, 0.03125. We actually have to memorize these up to 5 levels, 5 decimal places: 0.5, 0.25, 0.125, 0.0625, 0.03125. So the first thing that we would have to do is to find the equivalent of the number given in fixed point, where the point would be at its location fixed, and then we will be looking after this whole part, we will be fixing this whole part on the left, and then the decimal part which we will be fixing on the right. So let's say, for example, we have got this 19.1875. First, we have to realize that how we would work out this 1875. 1875 you can easily find by having these two 0.125 and 0.0625. Let me remind you, on the right side of the when we add on the right side, we add this way. Here we align numbers on the left, and when we add on the left side, we align number on the right. So if we add this, this would become 8 6, and that is how it will be. So if it is 0.125, 0.0625, this would become 5781. All right. So we add this way, and we align left. So we go by taking that rule. 0.1875. How do we find it? 0.125, 0.0625. All right. This you would have to do yourself. So remember these 0.5, 0.25, 0.125, 0.065. Unlike whole numbers where we have to complete the byte by putting leading zeros on the left side, here the significance of filling the whole byte is not that important. Okay, so we don't have to. So we would not have any leading zeros here or trailing zeros here. All we have to care is that what is the least amount of bits in binary we require here. So this is 19, 1, 2, 4, 8, 16, 16 and 2, 18 and 1, 19, and point 0011. 11 represents what, that we are actually adding 0.125 and 0.0625. So this representation is actually fixed point. Alright. So whatever number that is given, you would have to find out what is the equivalent of this fraction on the right by having these decimal places it, and on the left it would be the usual business. Now now we have to move this point, and we have to record that how many places we move this point. Before we go any further, we need to understand this formation. See how, let's say I have got this 0.5, 0.25, 0.125, 0.0625, 0.03125, 1, 2, 4, 8, 16, 32, and 64. Let's say I have got this number 10.25. I will 8 and 2 10. So this would become 1 0. 0.25 would be 0 1. Alright, this is usual description of it. Now, if I like, this is what? Fixed point. I have to convert this fixed point to floating point. When I'll float, it means that I'm floating this point outwards. But before that, let's discuss this. So let's say I've got 2000. I can write this 2000 this way, 2 into 10 power 3. Is that correct? Okay. So this 2 into 10, what do we call this? What is that? Exponent. What is this? Anyone? Base. Because the number system here is actually what? Base 10, which is January. Now what is this? There might be several names. The name that we gave it in our syllabus is Mantissa. Alright. So this multiplication symbol and this base is fixed for our number system. Similarly, for this number system, which is binary, base will be changed to 2, and this multiplication system, I mean symbol, will remain there. That means what is actually happening here, that we move the point from this location to this location. Alright. This exponent is actually how many times we have moved our point from this location to this location. We have moved it 3 times. That's why we put exponent 3. Similarly, over here the rule says that you have to move the point no matter what, all the way to the left, all the way to the left. So this would become 0.101001. I have removed the point from this location and I have moved it to the left. Okay. Now, why I have moved it to the left all the way? Because of few reasons. Let's discuss those. In computer science, we cannot represent the number with multiplication and two base and all. So what we do, we have this formation. We have this formation. This formation is actually called floating point, and in Visual Basic we call this what? Single or double at a time. Now what happens that out of these bits, few of the bits are allocated for exponent and few of the bits are allocated for Mantissa. This whole one big large combination of bits, out of which we have few bits allocated for Mantissa and few for exponent. Now this division is actually purely at the discretion of examiner. They will tell you, okay, how many bits are allocated in exponent and how many bits are allocated in Mantissa. By the way, this exponent may be found on the left side of Mantissa, but I haven't seen any such question yet. But if it appears that way, anyway, these are two different numbers, so they may be in any arrangement. So why we have moved the point all the way out? Because we cannot actually uh, have allocated space for this point or this multiplication symbol or for this base symbol. So what actually happens that it is assumed that the point or radix lies between first two bits. So when we move the point all the way out, it would become 0.1. It means that point now lies between first two bits. So there we go, first two bits. Alright. So when it is confirmed that point lies between first two bits, we don't have to actually show the point. It is understood that point lies between first two bits. Okay. Now Mantissa is actually always in fractions, because the formation of Mantissa, we talk about it um, a bit later. and exponent is always integer. What is exponent? Exponent is the number of times we move the point from its original location left or right. If we move it left, it means the exponent would be positive, so that in order to get the original number back, we will move it right. And if we move the point towards the right, exponent would be negative. Why? Because in order to get the original number back, we would have to move the point towards left. So positive, negative exponents we will discuss later. At the moment, our exponent would be positive. Since the exponent is the number of times we have moved the point towards the left, it would be integer because we are moving in whole number format 1, 2, 3, 4, 5. It is not 1.5 or 2.5 or something like that. Both Mantissa and exponent are in 2's complement form, means whatever the leftmost words will be, that will be negative, as in 2's complement. Acha. Mantissa is filled left to right, whereas exponent is filled right to left. So let's say that we have got more bits available and we have got a shorter number to fill in. So we will fill as much as we can, and after that all leftover bits will be filled by 0. Similarly in exponent we will fill it from right to left and all the leftover bits will be filled by 0. Now let's say in another case we have got more bits to fill and less space. In that case, we will fill as much as we can, and rest of the bits will be dropped off. We are filling in from left to right, and we are short of space. All of it is now wasted. Okay? Whatever the bits these are left are wasted there. It is not like if, when we are filling in Mantissa and we find less space, we get into exponent. No, that would not be the case. Similarly, in exponent, if we have got more bits to fill and less space, we'll drop it from the left. So extra bits will be dropped in Mantissa from the right. Extra bits will be dropped from the exponent on the left. And point always lies between first two bits. So so that point lies between first two bits, we move the point all the way. Now, so how many points we have moved? One, 2, 3, 4. So that will be like multiply by 2 to the power 4. Okay. Now this 4 needs to be converted to its equivalent binary form. So this would become 0, 1, 0, 1, double 0, 1. I have not put point here because it is now understood that point lies between first two bits. Similarly, I don't have a space original floating point to represent this multiplication symbol and this base, so it is understood. So after a little gap I'll be putting in 1, 2, 4. This is exponent, but I would have to put a 0 here because if I don't, this would become 1, 2 minus 4. We know that it is 2's complement. Okay, I hope that we all know what 2's complement is, right? Okay, now this is the floating point. This is called Mantissa. This is our Mantissa. This is our exponent. With the point lies between first two bits. Now after that you will be given the number of bits of Mantissa and number of bits of exponent. So let's say we have got 10 bits here. This will be given. It is not assumed. And let's say 6 bits here. Now we will start filling it in from left to right. 0, 1, 2, 3, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have got originally 7 bits that we have filled 1, 2, 3, 4, 5, 6, 7, and rest 3 bits because we have got 10 bits of space we will be filling in with zeros. Similarly, in exponents, we would have to fill from right to left. And how many bits do we have? 6 bits. So we will start with 1, 2, 3, 4, 5, 6. That's your floating point number. Is that understood? All right. So let's get to this one, 19.1875, and we realize that this would be 10011.0011. All right. So now we have moved the point all the way towards the left. That is a rule. Zero, that makes it 0.100110011 into 2 to power 5. Now we don't have to store this point or this multiplication or this base, so we remove all this and this becomes 0 1 0 0 1 1 0 1, and this 5 would become 124 01 01. Now we have to fill it with 10 bits Mantissa, fill it in 10 bits Mantissa and 6 bits exponent. So we'll start filling it from the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fortunately, this is 10 bits original and 10 bits space that we had, so we filled it in. And then we had 6 bits. So 1, 2, 3, 4 here and 5, 6. So this is it. This is actually the floating point of 19.1875. Alright. So let me revise this all. When a floating point number is allocated, a floating point data type is allocated, a large number of bits is allocated in computer's memory, out of which few bits are for exponent and few bits are for Mantissa. Okay? So we don't have a space for point, so we assume that point always lies between first two bits. Point always lies between first two bits. So we have to move the point all the way towards the left so that we have got point between first two bits. That is how we get it. Right? So when we move the point, we have to take this into account, that how many times we move the point towards the left. So that will be called our exponent. And our number system is binary, so the base is 2. So that makes this number this. And afterwards, we remove point, multiplication and base, and we keep the rest. And when we are given the number of bits from Mantissa and exponent, we fill that in. We always fill from left to right and right to left. Now let's talk about this uh, allocation of bits. Mantissa is in fractions and exponent is in integer. Integers we have been doing in O levels, we have been doing in AS, they are the same. Only exception is that this integer is now 2's complement. So whatever the most significant bits worth will be, that will be negative. Alright. So in Mantissa, what actually happens, in Mantissa we have this part in Mantissa, because point lies between first two bits and Mantissa is growing on the right, so we have always 1 on the left because point lies between first two bits. So on the left of the point this is 1, and on the right of the point this is zero point 0.5. So when it grows this way, it means that if Mantissa grows, only smaller fraction grows. Alright. So since it is in 2's complement, so this 1 would be negative. This 1 would be negative. On contrary, if we take exponent, exponent is this, is growing from right to the left. So whatever the most significant bit is, that will become negative. Alright. So this is our exponent, this is our Mantissa. Okay. So Since first two bits are actually having this point in the middle, so this would be the formation. So it will grow from left to right, and one would be negative one, whereas this one is, that depends, okay, what, how many bits do we have, and the leftmost bits what will be negative 10. So fractions are dealt by floating point unit in modern processors, as ordinary ALU is unable to handle these. So we know that we have got ALU, and ALU is considered as the hand of the microprocessor. So whatever calculation that is happening, that calculation is happening with the help of ALU. I mean, um, the part of the processor that is considered as the hands of microprocessor. But the thing is that ALU is unable to tackle these real numbers. We used to had this math processor in older generations of computers in 286, 386, 486, and then Pentium onwards they started making this FPU, floating point unit, and they inserted that FPU inside the same jacket as your processor. So now the same processor is harboring FPU. These modern computers nowadays are having like two or more FPUs in it. So all the fractions, all the real numbers are actually stored, they are actually being dealt by floating point unit, okay, and not by the arithmetic and logic unit. Okay. Now try solving this 36.5625. You will easily get 36, 32 plus 4, but how you will get 5625, right? यार ये फ्रंट वाली लाइट्स बंद कर दें, ये जो लाइट्स 36.5625. So we have this 36.5625, and this is a positive number. Remember to put this sign. These are always signed. So 36. How do we get 36? 1, 2, 4, 8, 16, 32. That is 36. 32 plus 4. 1, 2, 4, 8, 16, 32. 32 plus 4, that is 36. 5625. How do you get that? Zero point 0.5 plus 0.0625. Zero point 0.5 plus 0.0625, that becomes 5625. So that would be 1, 0, 0, 1. Alright. Afterwards, we move the point all the way to the left. So this would become 0.100, 100, 100, 1. And how many points we have moved? 1, 2, 3, 4, 5, 6. That would become 2 power 6. Now we will remove this point, as the point always lies between first two bits. Multiply and 2. 0, 1, 0, 1, 0, 1, 0, 1, and then 6. 1, 2, 4, and then 0. Now they say that you have to fill it in 10 bits Mantissa and 6 bits exponent. 10-bit Mantissa would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This bit got dropped because we don't have a space for it. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We don't have a space for this bit, so it is dropped. And then we have 6 bits here. So from right to left, 1, 2, 3, 4, 5, 6. That's your answer. What we lost? We lost 0.0625 because that was the bit here. Which bit was it? 1001. So this one we lost here. So when we turn it back to original form, this would become plus 36.5. Right? So mind it that the chances of losing fractions, or let's call it perfection, in floating point is high. In any other number format, we do not lose perfection or any shape or any worth, but in floating point there is always chance, right? So we may lose perfection. And what is the reason? There is one single reason, that is uh, not enough space. If we have got less space, we tend to lose perfection. All right. Then now let's say if we have got this number given, we are not given denary number, rather we are given what? Binary number, and binary floating point number. So we would have to do it other way around. All right. So let's see how we do that. Let's start solving this number onwards, the same number. So this is 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0. What we do, we go from this step to this step. That is 0.1, we know that point lies between first two bits, and then 001, 001. Don't need these trailing zeros here because they do not worth anything. And then into 2 to power, this is what? 124. 4 plus 2, 6. And then one step up means we have to resolve this part, the exponent part. So how we would resolve it? By moving this bit, sorry, point 6 positions towards the right. So 6 position towards the right would be 1, 2, 3, 4, 5, 6. Means point will go back this particular location. So this would become 0.00100.1. And if we put the whole thing back, this point 1 means point 0.5, and rest would be 1, 2, 4, 8, 16, 32. So 32 plus 4, that becomes 36.5, and we have to put this plus. So you see, original number was 36.5625, and we lost what? 0.0625 because of the less space. So not necessarily the number that you have will be coming back, because the reason is that if you have got less space, we tend to lose fractions there. Is it understood? Now, so we conclude that these floating point numbers are non-reliable if used for financial data storage, as larger fractions tend to lose accuracy. Floating point mostly are used in stats, graphics, real data types, and gaming engines, etc. Mainly, they are still used. They are still used, but the amount of space which is allocated is now higher, so that they do not lose any perfection. All right. Now we know how to convert a positive floating point number, positive decimal integer, sorry, decimal real number into a binary floating point number, and vice versa. Let's go further. Sometimes we have got negative floating point numbers. All right, negative floating point numbers. So how do we deal with them? Negative floating point numbers. For negative floating point numbers, see, let's say you have negative 10.75. All right. In that case, what we do, we just ignore negative and we solve it like we are solving positive number. So first we will be solving positive 10.75. So how do we do that? Let's make 10 first. 1, 2, 4, 8. That is 10.75 is 1 and 1. Afterwards we move the point all the way towards left, and that would be 0.101011 into 10 to power, sorry, 2 to power 4. And then afterwards we will write it 0101011 and 1, 2, 4. This is our floating point for what? Positive 10.75. In order to convert it to negative 10.75, what we do, we keep exponent the same to the first one. Remember the technique of two's complement. To the first one we keep Mantissa same and toggle or return rest. This is negative 10.75. In order to convert a positive floating point to negative, what we do, we keep exponent same, and in Mantissa to the first one we keep it same from the right side and toggle the rest, switch the rest. Okay, so 1 would become 0, 0 would become 1 would become 0, and onwards. Okay, so this is our negative 10.75. So whenever you have got a number which is negative and we have to convert it to the positive, sorry, we have to solve it to the floating point. So first thing that we will be doing is we are actually solving the positive number. Okay, and once we get the floating point for positive number, we keep the mantissa, sorry, we keep the exponent same, and mantissa to the first one from the right we keep it same and toggle the rest. So here exactly we are doing the same. This is minus 20.75. Ignore negative sign. Solve like a positive number. We solve the whole number. Okay, until here, and then we keep it same. And to the first one it is same, and rest are toggled. So this is actually negative 20.75. All right. Now, if we have got negative number given, and we want to solve it, how do we solve that? So let's say we have this one. First of all, we have to realize if it is negative floating point number, हमें कैसे पता चलेगा? By having this bit. Okay, अगर ये bit हमारे पास, if this bit is 1, it means it is a negative number, and if this bit is 0, it is a positive number. So if it is a negative number, it means that first we have to turn it to the positive number so that we could find that what is this negative number in denary. So we keep again the same technique. We keep exponent same. To the first one we keep mantissa same and toggle the rest. Now we have got this positive number, and then we will write it 0.101101 into 2 to power 4. And in order to resolve this 4, we will move 4 points right. This would become 0.1011.01, and then we solve it further. This would become 1 2 4 8, 8 and 2 10 and 1 11.25, but this is positive 11.25. It means the number that we were tackling was actually negative 11.25. So this is actually negative 11.25. Is that clear? All right. So when you have a floating point in binary, first you need to understand that if that number is negative, how do we find it if it is negative? By having a look at the leftmost bit of the mantissa. If the leftmost bit of the mantissa is negative, sorry, 1, it means it is a negative number. First thing that you would have to do is to convert it to the positive form. How do we convert it to the positive form? By having this exponent the same, and in Mantissa to the first one from the right we keep it same and toggle the rest. Once we do that, this is a positive equivalent of this negative floating point. And then we put point between first two bits, as it is confirmed that point always lies between first two bits, and then we solve the exponent in this form into 2 to power 4, and then we move the point all the way towards, or not all the way, as many points as mentioned in exponent to the right, and then we would have this number. And when we solve this number as in fixed point, there we go, we have got a number in positive form. If this number is positive and the original number was negative, it means it is equivalent negative number, that is 11.25. Now here we have got this number, we don't know what this number is, but surely we know that this number is negative. The first thing that we do is we turn it to from negative to positive floating point. We keep the exponent same to the first one, we keep it same, and we toggle the rest. Once we do that, we have got this number, and if we turn this number to the positive form, this would be 10.5. So this was actually negative 10.5. Alright. So try solving all these numbers now. Let's just solve A, B, C, and D. One positive, one negative in binary, one negative, and one positive in binary. Alright, let's move on. Now, normalization. What does that mean, normalization? We have realized one thing as of yet, that if we have got less space in Mantissa, we are going to lose accuracy or perfection. We do not lose majorly any number, but we lose the number as in uh, the fractions, smaller fractions. Okay? There are a few remedies, out of which one is the part of your syllabus, and that is called normalization. So normalization is a way to find more space in Mantissa, so that if you are losing any fraction on the smaller side, you can actually accommodate it. Normalization is a way to find more space in Mantissa. So what is normalization? Normalization, cannot save non-normalized floating point number. Normalization is an attempt to make floating point more accurate by having more space in Mantissa and reducing a chance of bit drop. Due to normalization issue, computer cannot save a zero. In order to have a zero in fractions in real numbers, you have all zeros in Mantissa and you have all zeros in exponent. Now, normalization says that if first two bits are the same, if first two bits are the same, computer would not save this number. Similarly, if it is this is considered as non-normalized. If first two bits are same, it is considered as non-normalized. Right? If it is non-normalized, computer is not going to save it. It is not necessary that first two bits are 0. If it is first two bits are both ones, it is equally non-normalized. Alright? So if we have got this situation, this number is said to be non-normalized as first two bits are the same. Computer will not save this floating point number. So what do we have to do? We have to actually, so let's say we have got this number. First we have to mark from the start which two bits are different. We can understand that first two bits are the same, so this is non-normalized. So we have to normalize it. In order to make it normalized, what we do, we first mark first bit and the bit which is different than first bit. It might be 0, it might be 1 and 0. So yeah, if it is starting with 1, then we will look for 0 there. If it is starting with 0, we'll look for 1 there. So in between these two different bits, जो भी हमारे पास बीच में different bits हमारे पास आते हैं, we will take these bits out. सही है? This will be taken out. Rest will be shifted. Means rest means these. From this point onward, this point, they will be shifted to the left, and zeros will be filled. This space found on the right side. So 0 and 1. Now this 0 is this one and this one is here. Alright? 0 and 1. And then 0, 1, 0, 1, 0. These are original. So how many bits were originally there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many are these? 1, 2, 3, 4, 5, 6, 7. This way we found out how many spaces? 3. And these 3 spaces will be filled by 0. Okay? Acha. These bits are shifted, 3 spaces are found, these 3 spaces will be filled by 0. But what would be the effect? Effect would be, earlier this was actually going 6 places left, and since we have taken out 3 bits, we would have to adjust this exponent accordingly. So we would have to subtract the number of bits we have taken out from the exponent. We have to subtract the number of bits we have taken out from the Mantissa in exponent. So how many bits we have taken out? 3. What is exponent? 6. So we actually subtract 3 from 6. So the number of bits taken out will be subtracted from the exponent. Okay? So we fill rest with the zeros, and this would be now 3. Earlier it was what? 6, and now it is what? 3. Is it understood? Okay. This is normalized now. Achha. Now, several times in past papers, a question appears that says how these two numbers, which is non-normalized and normalized, are equal. So you have to solve both side by side to tell that these two are actually the same, whether it is normalized or it is non-normalized. Since we adjust this exponent, there is no difference in the number. Let's see how. So if it is the number and we try to solve it, this would be 101.01. This becomes 5.25, and this is a positive number obviously because we have 0 on the left. So if we take this normalized form, as in here, we solve it, this would be 5.25 as well. So they both are same. The normalization does not affect the worth of the number, only it finds more space in the Mantissa. They both are the same. Okay. Try solving this number. Tell me what this number is. This is a negative number. So first you have to mark first bit and the different second bit, which is this. So these two bits will be taken out and exponent will be adjusted accordingly. Afterwards, आपको क्योंकि नेगेटिव नंबर है, आपको पहले इसको पॉजिटिव कन्वर्ट करना पड़ेगा and then you will solve it. Let's see what you do. This is negative non-normalized number. Negative non-normalized number. Alright, so how do we realize that if this number is non-normalized and if this number is negative? So whenever you are given a binary floating point number, first you have to check if it is non-normalized. So since it is non-normalized, first we have to normalize it. So how do we normalize it? First we mark that which two bits are different so that we could take out bits in between. So how many bits we are going to take out? 2. So now this would become 1010110. And how many spaces we found out because of the removal of this 2 bits? 2 spaces. So we will fill those 2 spaces with zeros. So this is one thing that you have to understand. Few people think that since we are removing ones, we are going to put ones there in the empty space. No. If it is 1 or negative number or positive number, in any case, whenever we have a new bit, you will fill it with zeros. It really does not matter if it is now negative or positive. So we have to fill it with zeros. One thing. How many bits we have removed? 2. The original exponent was 4. So what is left? 2. So this would become this 010. Now you have to check that this particular number is negative. So what we have to do? We have to turn it to positive. So exponent remains the same. So the first one, Mantissa remains the same, and rest are toggled. So the number becomes this 0101110, and then solve it 0.1011 into 2 to the power 2, and then we have this. We have to move this 2 positions to the right. So this would become 10.11, and this would become what? 2.75 making negative. Is it clear? So whenever you have got a negative number, whenever you have got a binary floating point, first you have to check if it is normalized or not. If it is not normalized, normalize it first, and then you have to check what is the power. If it is what is the sign? If it is positive, go on. If it is negative, turn it to positive first. All right. First, you turn it and then solve it. Once you have got the answer, put a negative sign there. If it is a negative number, if it is positive number, leave it like that. आगे समझ लो. हाँ. We have to subtract the number of bits we have removed from the mantissa from exponent. So if it is 2, exponent is 4. 4 minus 2 becomes 2. Let's say if it was 7, we remove 2, it would become 5. Alright? Exponent is what? Exponent is the number of positions we move the point. Since we remove those positions, you have to adjust the exponent accordingly. Give it up. Negative, see, the original number was negative. We turned it to positive and then we solved it. Exponent अगर negative में आ रहा हो तो फिर भी add होगा ना. Negative negative हो जाएगा. Just leave that. That is not part. हम उस पर बाद में डिस्कस करते हैं. थोड़ा सा रुक जाइए. You mean this? One, 1, 1, 0, 1, 0, 1, 0, and then you have minus 4. This is what you're talking about, right? Okay. If you remove these two, okay, this would become 101010, and what is exponent? Minus 4. All right. So actually, point was meant to go on the right. Sorry, on the left. All right. Let's just don't normalize it. Let's just solve it first. What is this number? So we keep exponent same. To the first one we keep it same and then toggle the rest. Right? This would become 0.001011 into 2 to power minus 4. You meant to go on the left how many times? 4 times, because your exponent is negative. That is why I said it will still be subtracted, because you have to go further. Alright, so this would become 0.1234 and 001011. This is your actual number. Alright, so you have to have this actual number back even if you remove numbers from there. Alright, so earlier it used to go 4 times. When you subtract, it would have to go further 3 times in order to get this number back. But since such questions do not appear, just leave it. But it was a good question. Anyways, now we have an idea how to solve positive, non-normalized, floating point numbers, and then we have to solve how did we solve negative, non-normalized floating point numbers. Okay? Now, two things. There are questions. What is the relationship between Mantissa and exponent? First of all, you need to understand that Mantissa is to accuracy, exponent is to the range. Mantissa is to accuracy and exponent is to the range. Acha, this range is also called sometimes size. Why size? Because if we have got a bigger exponent, we have a number which is actually higher in worth. Size of the number grows. Okay? And secondly, let's say that this is a bar, a slider bar. If we move this bar towards accuracy, it means that we are reducing accuracy but we are increasing the size. And if we are moving this slider towards the right, we are increasing accuracy but we are reducing the size of the number, possible biggest size of the number. This is very important to understand. So what is the relationship between Mantissa and exponent? What is this called? Inversely proportional. If we increase the Mantissa, we reduce the exponent, or we can say that if we increase accuracy, we compromise on the size. Why? Because the size of the whole floating point is fixed. We have got, let's say, 16 bits and 10 bits for Mantissa and 6 bits for exponent. If we are reducing exponent, which means that we are increasing Mantissa, because we are not going beyond 16 bits. 16 bits are there, they are fixed. If we are reducing exponent, it means that 6 bits are now like 4 bits or maybe 3 bits or 5 bits, whatever, and we are increasing Mantissa. If we are increasing Mantissa, we are increasing accuracy. Okay? So this is inversely proportional. The relationship between exponent and Mantissa is inversely proportional. If we increase accuracy, we compromise on range, and if we increase range or size, we compromise on accuracy. Alright, so these are other 3 questions. You can solve it later. These slides are already uploaded. I hope that you know that I have uploaded the resource pack lately on the group and event. It is pinned on the top. The group is zakonweb.com/free group. It is pinned on the top so that you could download these slides. Right, these slides are uploaded. So the last thing, what if your number is in fractions only, in 0 point something? All right, so let's say, how do we actually solve it? Let's say we have 0.25, we have to solve it. How do we solve it? It means, let's say we have got 6 bits in Mantissa in 4 bits. Let's make it 8. 8 bits in Mantissa and 4 bits in exponent. 0.25. First, we have to convert it to. So 0.25 का मतलब ये हो गया, we have got this point here, 0.5, 0.25, 0.125, and further over here we have got 1248 further. So 0.25 means we don't have any figure here and we have this. Alright, so this would become 0.01. That understood? So do we have to move this point anymore? No, we don't have to, because we don't have anything on the whole side. So what would be exponent? Exponent would be zeros, because we don't have to move the point. So this would become what? 0.01 into 2 to the power 0. This would become 0, 0, 1, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4. Is that correct? No. Why? Hmm? Yeah, we have to normalize it. I thought you people are saying that it is converted wrong. It is converted alright, but what we found on the way, that it is non-normalized. Computer will not save it, so we have to normalize it. If we normalize it, this would become 0, 1, 2 digits, sorry, 2 bits, 1, 2, 3, 4, 5, 6, 7, 8, and 0 minus 1 becomes what? Minus 1. So minus 1 would be this. This is minus 1 in 2's complement. Alright, now this is the correct conversion of point. This is equal to 0.25 positive 1. You get that? So whenever you have a decimal number which is in fractions and there is no whole part to it, the floating point that you will reap out would mostly be non-normalized. Is it understood? Whenever we have got a number which is less than 1, there are chances that the number, floating point number that we get would be non-normalized. So we would have to normalize it. Alright, so let's try this. Normalization. Normalization obviously would come here. This would become 0.1, and if it is 8 bits and 4 bits, then 1, 2, 3, 4, 5, 6, 7, 8, and then 4. 1, 2, 3, 4. Alright, a mouse move कर रहे हैं, ठीक है? This is positive 0.5. ठीक है? It is normalized and it is perfect. But original number was minus 0.5. So we have to convert it. So we keep exponent same. To the first one we keep it same and toggle the rest. Alright? 1, 2, 3, 4, 5, 6, 7, and toggle the rest. As soon as we convert it to negative form, this is now non-normalized. If I like to normalize it, this would become 1, 2, 3, 4, 5, 6, 7, 8, and this would become minus 1. Alright? So that's it. That is how you did it? All of you? Okay. Now, So get the idea of normalization now, all of you. Now next, range. Range means in a given amount of bits, what is the highest, what is the lowest, both in positive side and negative side, floating point that you can reach. What is the highest positive number? What is the lowest positive number? What is the highest negative number? What is the lowest negative number? Now, before we go any further, we now understand that we cannot save 0 in real numbers, because if we like to save zeros, we have to have all zeros in Mantissa and all zeros in exponent, isn't it? So all zeros in Mantissas are not allowed. And what computer does? Computer actually saves the smallest positive number as 0. What computer does? Computer saves smallest positive number as 0. So it means that 0 does not have its representation as an actual, and there is a makeshift arrangement. That is another reason you cannot say that floating point is perfect, right? So you would have to remember this grid. This is necessary. How to find the largest positive and how to find smallest positive, largest negative, and smallest negative. So first have a look here. On the left of 0, it is all negative numbers, and on the right, it is all positive numbers. This 0 is fictitious since it is not saved. Largest negative number means smallest magnitude. Largest negative number means smallest magnitude negative number. You might not have the term largest negative in exam, rather you might have the term smallest magnitude negative number, which would actually be the largest negative number. And similarly, smallest negative number is the number with the highest possible magnitude. But this is solved on the left. Smallest positive number we know, and then largest positive number we know. Alright. So how do we achieve it? Here I have explained it using 4 bits in Mantissa and 4 bits in exponent. But you might have as many as 8 bits in Mantissa and 8 bits in exponent. So what does that all mean? They'll give you that you have as many bits in Mantissa and as many bits in exponent, and you have to tell what is the largest positive number, what is the smallest positive number, what is the largest negative number, what is the smallest negative number. Alright? So you would have to memorize all these. In order to get a largest positive number, you have to have a largest positive Mantissa and largest positive exponent. Why do we have these zeros on the left? Because this is -1 and this is 1, 2, 4, -8. These are two's complement. So in order to avoid any negative number there, we have to actually have positive numbers. So if it is 2's complement and we need to know the largest positive number, we have to avoid the 2's complement side. Alright? So if we solve it, this would become largest positive number 0, 1, 1, 1, 1 in 4 bits Mantissa. And actually what you have to do, let's say if you don't have 4 bits, rather you have 10 bits. So you will take the rightmost bit here, you will fill it up further. Rightmost bit here and fill it up further. Rightmost bit here, here, and fill it up further. Same goes for exponent. If you have got more than 4 bits, take this bit, fill it up on the right side. Is that clear? So if you have got 2 bits, cut these two, this would be 0 and 1. So let's say these are normalized Mantissas. These are non-normalized. And these smallest positive and largest negative normalized Mantissas are actually roughly normalized. They are not actually normalized. Uh, these are not actual representation, because smallest positive should be with the one here, not there. See, zero point 0.5, 0.25, 0.125. Smallest positive has to be what? 0.125. But that's 0.125 would not be normalized. We put 1 here. If we put 1 here, then this 0.125 plus zero point 0.5 becomes 0.625. That is not the smallest positive. So if we remove that one here. So all those rough reasons, I would only say that try to memorize this. This is roughly normalized. These two. In order to have the largest negative is the smallest magnitude number, you have to have all these ones, you know, all these ones, because putting all these ones would not make it normalized. It will make it non-normalized. We deliberately put a zero there. Just try to understand that you have got just one way out, that is to memorize these. Okay. Alright, let's just solve all these with 4 bits Mantissa, 5 bits Mantissa and 3 bits exponent, let's say. The 5 bit Mantissa means we will extend this one. Okay. So 0, 1, 1, 1, 0, 1, 1, this is 0.1111 into 2 to power 3, and that has become 7.5. So the largest number that we can save in 4 bits Mantissa and 3 bits exponent is plus 7.5. Remember to put the sign. And then smallest positive number, we take 0, 1, 0, 0, 0 as 4 bits, and then 100, that would become zero point 0.1 into 2 to power minus 4. So you take the point towards the left. Why? Because the exponent was negative this time, and this has become 1 over 2 to power 5, or 2 to power minus 5. You can leave it here, you can leave it here, and if you like, you may solve it. Alright? You can leave it here, here, or here. Everything is accepted. Alright? What I will do, I'll extract this lecture and I'll make it available online. Alright? If you like, you can hear these lectures back to the day of exam. You would have to request it in personal. जो हमारा WhatsApp number है उसका मुझे personally भेज दीजिएगा. I'll share these lectures online so that you could hear it back. Okay? Alright. Then largest negative. Largest negative means 10111 and 100. Means 10111 and 100. This is a negative number, so we have to first convert it to the positive, and then to the first one it is same, and rest are toggled. So this would become 0.1001 into 2 to power minus 4. Point goes further, this has become 2 to power minus 5 plus 2 to power minus 8, and the sign is negative because of this. You don't have to solve it further. If you have will, you may go ahead, but calculator will not be allowed. Okay, you can leave it here. Smallest negative, this is negative 1 into 2 to power 3. Alright, so this is negative 2 to power 3, means minus 8. Is it clear? So the smallest negative number is the number with the largest positive magnitude, right? So minus 8 is the smallest number, minus 2 over minus 5 plus 2 power minus 8 is the largest negative number. Smallest positive numbers would be 0.03125, and the largest positive number would be plus 7.5. You would have to practice it. Now, this is important because there are a couple of instances when they actually ask for ranges when you have 8 bits Mantissa and 8 bits exponent. When it comes to 8 bits Mantissa and 8 bit exponent, we are certainly dealing with large numbers or very small numbers. In that case, we have to use assumptions because calculator will not be allowed. Let's see how. The largest positive number will be here and here. So we assume that with all these zeros, sorry, all these ones on the right side of point will become what? 1. And 1, 2, 4, 8, 16, 32, 64 becomes 127. It means that point will travel 127 times on the right, so we cannot actually solve this figure. Or that would be a larger figure. Calculator is not allowed. So we assume that all these ones here are actually a 1. Could be a little lesser than that, but since we have some compulsion, we are not going to solve it like that. So this is plus 1 into 2 to power 127, and this becomes plus 2 to power 127 as a rule of thumb. That's it. All right. So if it is smallest positive, we take the same, we extended zeros and all, and this would become zero point 1 into 2 to power minus 128. 2 to power minus 128. So we have to move the point all the way towards the left 128 times. That we cannot do. So what we do is solve it. We move the point towards the right. Minus 128 minus 1, this becomes minus 129. And 1 into 2 to power minus 129, and that is 2 to power minus 129. You would have to rather remember this than solving it. Largest negative is solve it like that. So this is a negative number, so we keep the mantissa same, sorry, exponent same, and to the first one we keep the mantissa same and toggle the rest, and this would give us 0.1000001 into 2 to power minus 128 means this number, means this number, means this number. All right. And then the smallest negative, this is negative 2 to power minus 127. This is negative 1 anyway, isn't it? Negative 1 multiplied by 2 to power minus 127, that has become what? Minus 2 to power 127. This is negative 1, Hassan. This is negative 1 minus 1. Minus 1 multiplied by 2 to power 127. This has become what? Minus 2 to power 127. Alright? This is explained in the book as well. Now, the last part. Any question? If you won't practice, you won't get it. Let me tell you. In normal classes, I have to teach it like 6, 7 times. Every second, third month, they ask me, sir, ek baar dobara karwa do. So still you would have to. There is one question coming out of this topic, and there is no way out. So practice all of whatever we have discussed here. Now, there are errors called accuracy errors or whatever you call, that we have to understand in terms of programming. Which data type corresponds floating point? Single. So let's say I've got this new project. Alright, let's say I have a variable a which I have declared as single, means it is floating point. The value of a is, let's say, zero point 0.3, and then I have got another variable index as integer. So for index is equal to 1 to, let's say, 25, and a is equal to a plus 0.1. Console dot write line a. Let's see what is the result. So console dot 80. Do you see any error at any point towards the end and at the start as well? Why do we see such errors? This is not reliable. Okay, what I have done? I have done what? Check. Nothing. I just added zero point 0.1 to it. I started off from 0.3, then I have got zero point 0.4 perfect, 0.5 perfect, 0.6 perfect, 0.7 perfect, but zero point 0.8 what? Why it is? What computer tries in modern languages, it tries to overcome the error which is building. But when the error becomes significant, it cannot control it. So it just output it, shows it. Then it goes okay with it for little time, but then error accumulates once again. So there we go. It has to be 2.8. Why the error is so small? Because it is in fractions. Sometimes we are losing fractions, sometimes we are gaining fractions, but it is not actually perfect. Is it clear? There was a question in past paper exams. What is happening? Why this output? So you would say that rounding error. These are called what? Rounding errors. And why do we have these rounding errors? For the reason that we are losing perfection. Because when the number grows, we have got less space and we are losing perfection, and that error is being accumulated. Computer tries to overcome it. It shows perfectly, but at one given point, it actually and control it, it outputs. These are called what? Rounding errors. There is a website called, I don't remember exactly, floating point guide. Floating point GUI.de. So it was this, yes. Floating dash point dash guide. It is German website, .de. But it is a wonderful website. Go through this website, it will tell you more. This is a wonderful website. So go with this rounding errors and it will tell you so many things. You see, it is trying to explain why don't my numbers add up properly. If it is zero point 0.1 and zero point 0.2, why do I get this? So it is all explained there. Second thing, do make a note of this website, do visit it. Floating point guide. What if you like to save zero point 0.3? Would you be able to do so? No. So you would have to take a number which is closest, which is 0.25, 0.8, 0.75, 0.96, 0.75. Now, look at the difference. If it is 2.96, what I'll be saving? 2.75. Because between 0.75 and whole number, I don't have any denomination. So let's say if I've got 1 rupee and if I've got decimal number system, I can break that 1 rupee in 100 paisas. If 1 pound, then 100 pennies. If $1, then 100 cents. But if it is binary number system, what can I do? I can only break it in 0.25, zero point 0.5, whole number 0.75. I will not be able to solve any fractions in between. So I would have to take up closest perfect floating point number. One of the reason is that in denary number system we divide it by 10, so we have 10 denominations. In binary number system we divide by 2, so we have only 4 denominations. Is that clear? So do visit this website, it will clear your idea, and especially look for this rounding error thing. Do expect questions from this. Alright, large denominations, whatever. This would be, of course, uh, we don't have time to discuss it all, but you would have questions. So I told you about floating point as much as I can. All 360 degree, whatever that has appeared in past paper questions. And I showed you a program and I actually showed you the rounding error, how they are accumulated and shown. And I told you about this website. Rest is actually up to your practice.